Hello and welcome to the Math 200 lecture series for Cañada College. We are using PowerPoint presentations created from m200-Triola's textbook, Essentials of Statistics, 5th edition. My name is Lapuz. We are in Chapter 11, Chi-square and Analysis of Variance. Just as a review, we began our study of inferential statistics in Chapter 7 when we found confidence intervals. In Chapter 8, we started our hypothesis testing with one samples for estimating the proportion, the mean, and the standard deviation of a population. In Chapter 9, we extended those methods to involve two samples. And in Chapter 10, we studied correlation and regression when we have paired data. In Chapter 11, we'll focus on categorical data. So the data is non-numeric, it's categorical, or qualitative variables. We're going to take a look at hypothesis tests that observe the counts, and we're going to test claims about distributions on those categorical variables. We're also going to take a look at contingency tables or two-way tables, and our main focus, at least for the first two sections, will be on the chi-square distribution. Section 11-2, Goodness of Fit. The idea behind this section is to consider frequencies of some categorical variable. We will be looking at one-way frequency tables, and it's very similar to the frequency tables that created our histograms way back in Chapter 2. But our categories are nominal variable categories. They're categories that are non-numeric. We can also equate this into a multinomial experiment. Unlike the binomial experiment that yielded our proportion problems, we're going to be looking at possibilities where there's more than two categories. Instead of just looking at a success or failure, we're going to look at more than two categories. The goodness of fit test is a test that observes the frequency of a distribution if it fits to some claimed distribution. We're going to focus on two types of tests here. One test is that the distribution is all even or uniform. That's the case where all the categories are equally likely. And then the other half of it we'll be looking at when there is some other claimed distribution that is involved. The requirements for the goodness of fit test are similar to the ones we've had in the past. We need a sample that is simple and random. The sample data consists of frequency counts for each of the different categories. So those will be our observed frequencies. We'll take a look at that. And then for each category, we have an expected frequency that is at least 5. We will be using a test statistic that involves a formula, and the formula will need these symbols for our notation. O will represent the list of numbers that are observed from the data. E will be the list of expected values that we would have, and the expected values would be based on a claim. K is the number of categories we have, and N is the total number of data, the number of trials. The goodness of fit test has a basic set of hypotheses. The null hypothesis would be that the frequency counts agree with some claim distribution, whether that claim distribution says that everything is equally likely in the category, or each category has its own percentage or proportion or probability that is mentioned in the claim. The alternative hypothesis says that the frequencies do not agree with the claimed distribution. Our chi-square test statistic will be the sum of the list of observed minus expected frequencies quantity squared divided by the expected frequencies. So we will talk about how to compute this with our calculator. Some calculators allow us to find the p-values, and there's other calculators that don't have this advanced hypothesis test. But there are other programs that exist, and you can check the textbook and the website, the MyMathLab website, because they have a way for you to download that particular program. Without the p-values, if we're going to use the critical value method, we will be using table A4 because this is a chi-square distribution. And for using table A4, you need the degrees of freedom, and the degrees of freedom will be k minus 1, the number of categories minus 1. And the goodness of fit test is always going to be a right tail test. The observed frequencies are given as data that was collected. The expected frequencies will be something that you will need to find. And it will depend on whether your expected frequencies are assumed to be all the same, or if the expected frequencies are going to be different. If the expected frequencies are all the same, then each number in your expected frequency will be the total number of data collected, that's n, divided by the number of categories. So you're essentially breaking up the total number of data that you collected and distributing it among the categories. Now, if your expected frequencies are not all equal, then each category will have an associated probability p. And so you would need to find the total values and multiply the total by p for each of those categories. The general idea with this hypothesis test is that if you find a chi-square value that is small, then you're looking at a close agreement with the null hypothesis. If your chi-square value is large, then you're saying that you are disagreeing with the null hypothesis. So a significantly large chi-square value will reject the null hypothesis. And here's just a graphic of the last slide that we just saw. In general, we will be looking at some critical values to compare your test statistic. Or even better, if your calculators can work it out, we can find the p-values, and we'll use the same criteria that if we have a small p-value, we will reject the null hypothesis. Let's take a look at an example. We have a random sample of 100 weights of Californians obtained, and we will look at the last digit of those weights. When we found the weights, it's important to be able to tell whether the weights were reported or self-reported, or were they actually measured properly. So by analyzing the last digit, we can verify that the weights are actually measured, since most people usually round off to the nearest tens or fives, or zeros or fives. Like instead of somebody weighing 187 pounds, they would just round it off to 185 or 190. So here's our problem. We're going to test a claim that the sample is from a population of weights in which the last digits do not occur with the same frequency. So that's to say, we would be looking at zeros and fives popping up in the last digit. So here's our data, and just by an initial glance of the data, we see that the last digit of 0 occurs 46 times out of 100, and the 5 occurs 30 times out of 100, where everything else occurs in a single digits. So already it looks like we will be able to reject our null hypothesis because the frequencies are not all distributed equally. But let's actually go through the test. So let's do the requirement check. The data come from some randomly selected subjects. The data consists of counts, and with 100 samples, 10 categories are claimed are equally likely, so each of the expected values should be greater than 5. And so all the requirements are met. Let's go on and do the hypothesis test. Step 1, we want to find our original claim, and the original claim says that the digits do not occur with the same frequency. So what they're saying is that at least one of the probabilities is different from the others. The opposite of that is to say that all probabilities are the same. So we have a string of equalities from the proportion of p sub 0. That's the proportion that the 0 would pop up. P sub 1 would be the proportion of the number 1, the digit 1 popping up as the last digit of the weight reported, etc. In step 3, we organize those two statements and identify the null hypothesis as the one with the string of equalities, and then the alternative hypothesis is the one that says at least one of the probabilities is different. So our significance level is given to be 0.05, and we will be using a chi-square distribution for the goodness of fit test. So here is the hand calculation, or the calculation without using much technology. We have the list of digits given. We have the observed values in our second column. Now, because our 100 data points have to be distributed equally between 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and so there's 10 categories, we're going to take 100 and we're going to divide each one by 10, which is going to give us a value of 10. So our expectation, if this was all distributed equally, our expectation would be each of these observed counts should be about 10. Again, we have 0 and 5 that clearly stand out in the double digits where everything else is single digits, so this is probably going to reject the null hypothesis. But we'll continue on with the test. We have our expected values. The next column we have the observed minus expected values, which is a subtraction problem. 46 minus 10 is 36, 1 minus 10 is negative 9, etc. After we subtract them, we're going to take each of those numbers and we're going to square them. That's our next step. And then the observed minus expected quantity squared divided by the expected would be taking our last column, that's 1296, and we're dividing it by our expected value, which is 10. We got 81 divided by 10 for the second row, etc. So now that we have this O minus E quantity squared divided by E column, we're going to add them up, and that will give us the sum of our values. This is a really large number, 212, And so remember what they said, a large test statistic would mean that our test statistic is all the way to the right, and for a right tail test, there's a good chance that we're going to reject the null hypothesis. So we formally reject the null hypothesis when we find our critical value from table A4, and with a 0.05 significance level, we see that our chi-squared and our k-1, our degrees of freedom, is 9. We see that our critical value is 16.919, and our test statistic is way, way, way to the right. So we're going to reject the null hypothesis. So we reject the null hypothesis. We have a large chi-squared test statistic, and that would yield a very small p-value. And so when we reject the null hypothesis, we come to our conclusion. We conclude that there's sufficient evidence to support the claim. Remember, the claim was that the digits do not occur with the same frequency. And so because that's the alternative hypothesis and we rejected the claim, since our claim turned out to be the alternative hypothesis and we rejected the null hypothesis, then we can say that we actually support the claim. So in other words, we have evidence that the weights were self-reported and the subjects did not actually weigh what they reported. They rounded up to the nearest 0 or 5 for their last digit. Okay, that's the end of section 10-2.